Hello, class. Okay, so we're going to talk about logarithms and kind of keep this as simple as possible, just what we need for this class. And so to start out, let's say write down something like this. Like what does this mean? So you have logarithm, this a here. Now let me change it to b. So that's the base of the logarithm. And so we're saying like the logarithm to a particular base of x equals y. So, what does this mean? This means that b to the power y equals x. So this is how these variables b, x, and y are related. All right. Now, the base can be anything. You could have a base 10. That's a very common one. Another very common one is a base e, where e is that number. It's like 2.71. It's an irrational number. It keeps going forever. In that case, if you have a logarithm base e, say log base ex, that is its special notation. That's called the natural log. We use the notation ln. We're not going to actually use that here, though. We're only going to stick with base 10. So what I'm going to do is just write, now if we just see this, log x equals y, if the base is not given, now the standard convention is that we assume that's a base 10, if there's no base given. Now I say that's kind of the standard convention, but a lot of people don't follow that convention. And the reason why is the natural logarithm is by far the most useful. And it's used so often, where the other bases are rarely used at all, that a lot of books just, when they say log x, they mean natural logarithm of x. Because that's the only one anyone really uses, except for a few applications. But we're going to stick with the standard convention. When we say log of x, we mean base 10. So we don't have to write the 10 down. Okay, now what good are logarithms? Well, there's... Here, let me try to fit this. Say log x equals y. That would mean 10 to the power y equals x. Okay, so why do we define logarithms at all? The main reason that logarithms were developed is for calculations before the age of calculators and computers. It can make calculations much simpler. And that's because there's a few properties that logarithms have. Now, if you look at an algebra book, they say like there's 6 properties or there are 8 of them. Really, there's 2 fundamental properties. Let's see. I'm going to change, let's just say logarithm of a to the b. Or, sorry, logarithm of a times b. This is equal to the logarithm of a plus the logarithm of b. So that's one property. And then another property is logarithm of a to the power b and that would be b times the logarithm of a. So those are really the only 2 properties that we need. Now, if you look at an algebra book, they have more, but we don't really. Let's look at an example of something you might see. Logarithm of a divided by b. we don't need a special property for this because we can write this as logarithm of a times b to the negative 1 power. And then use this first property, logarithm of a plus logarithm of b to the minus 1 power, which is logarithm of a minus logarithm of b. And so that's a property, log a over b is log a minus log b. That's nothing new though. So really, this is all we need to know about logarithms. These three things. Probably the most difficult to keep in mind is this one, right? Just the relation between these variables. We're going to keep it a little simpler by we're only dealing with base 10. And so out of these, when you have like log x equals something, just think that what follows the equal sign is the exponent. So you take the base, which is 10, to the exponent y, and that's equal to x. Now, I want to look at some examples of logarithms. And we're going to probably do this we could do this in one line, but I want to look at a few examples. Let's say we have the logarithm of 10. What is that equal to? We don't know what it's equal to. So let's call it y just to be consistent with what we have over there. If logarithm of 10 equals y, that means 10, so base 10 to the power y, that equals x, which in this case is 10. And so we can easily see, 10 is 10 to the first power, so y equals 1. Okay, let's look at another one. Say log of 100. We don't know what that's equal to, so we call it y. And this would mean 10 to the power of y equals 100. And 100 we can write as 10 squared. So we can see y equals 2. Let's do one more, following the obvious trend here. What about the logarithm of 1,000? That's equal to y. So we can say 10 to the y is 1,000, which is 10 cubed, which would mean y equals 3. And so on. Basically, log 10 to the nth power, we can see that y equals n. Now, it's a very quick way we could see that. We can just kind of follow a pattern and see, well, yeah, that's how it's going to work out. We can write, here, in general, let's just continue the way we've been going. This would mean 10 to the y equals 10 to the n, which implies y equals n. There's another way we could do this. We could say logarithm of 10 to the nth power equals n times the logarithm of 10, and we can see if logarithm of 10 is equal to 1. So log of 10 to the n equals n. Now, we've been looking at 10 to a power, and specifically the power we've been looking at has been positive. 10 to the first, 10 to the second. What if we have 10 to the minus 1? I should have probably moved this down, but what if we have a logarithm of 10 to the minus 1? I'm going to write this off to the side. That's 1 over 10, which is 0.1. So the logarithm of 0.1 equals y, so we don't know what it is. That means 10 to the y equals 0.1, which we can write as 10 to the negative 1. And so y is negative 1. So that same rule applies. Log of 10 to the n equals n. That seems to hold up for negative numbers as well. let's do one more, just to be sure. 10 to the minus 2 is 1 over 100, which is 0.01. Zero should go both ways. That means 10 to the y equals 0.01, which we can write as 10 to the negative 2. So y equals negative 2. So it works for positive numbers, and it works for negative numbers. And one thing we left out, we're just dealing with integers right now. The one thing we left out is 0. What about log of 10 to the 0th power? Well, 10 to the 0th power is 1. So logarithm of 1 equals y. That means 10 to the y equals 1, which would mean y equals 0. So this general rule holds up. So we can write this down here. Log of 10 to the nth power equals n. That works for positive integers, negative integers, and 0. Another thing to note here is that let's look at one more example of logarithms. Let's erase all this. Let's look at logarithm of negative 4. We don't know what that is, so let's call that y. That means 10 to the power of y equals negative 4. And now we have a problem. Because, if we plug in a positive number here, like say a number greater than 1, like 10 to the power of 2, obviously that's going to be a positive number. If we plug in a negative number, maybe you think by making y negative we can get a negative number. But no, if we plug in, say, 10 to the negative 2, we're still getting a positive number. 10 to the 0th is 1. There's no way we can get a negative number here. So this just does not exist. You can't take the logarithm of a negative number. So, one more thing. Let's plot the logarithmic function, like a base 10 logarithm. So let's say we have x and logarithm of x. Now it's hard to fit this on scale, but let's put the number 1 here. See, the problem is, if this is 1, then 10 is way over here, and 100 is, way off the board. So, but I don't want to put 1 really, let's say this is 1, so maybe not exactly to scale. So this is kind of a very inaccurate picture, because obviously if this is 10, that's like 25, but can't really fit it on this scale. But what the logarithm, remember logarithm of 1 is 0. Let's say this is 1, this is 2. Logarithm of 10 is 1. Logarithm of 100 is 2. And if you go to like logarithm of, say, 0.1, remember that was negative 1. And 0.01 would be negative 2. And so it's very hard to really graph accurately how steep the curve is here and how flat it is over here. But basically, the logarithmic function looks like this. It's very steep. It crosses the x-axis, or the y-axis, sorry, at x equals 1. And then it's a very slowly rising function. So again, it's actually steeper than I drew it here and flatter than I've drawn it here. So this is the logarithmic, base 10 logarithm, not exactly to scale. Very steep here, very flat over here. Now again, what good are logarithms? Well, one of the main things I mentioned before is for calculations. Like, let me give you an example of how this would work. When we're talking about arithmetic, we have a hierarchy of difficulty. Like addition and subtraction are very simple. Multiplication and division are more complicated, and exponents are more complicated still. If you think about exponents, in some cases, exponents, like say 5 squared. That's just 5 times 5. That's simple enough. But if you have like 5 to the 7th power, you're multiplying 5 by itself 7 times. That's kind of cumbersome. And so exponents are more difficult. And a further complication is, what if you have 5 to the 7.5? How would you figure that out? Well, you can't really do it without logarithms. So exponents are the most difficult thing. And as far as like just doing arithmetic, exponents are very difficult. And then the next order of difficulty is multiplication and division. And the simplest is addition and subtraction. And what logarithms do is they just reduce the difficulty by one level. Like if you have something like this, let's say we don't know what this is, so let's call it y. If we take the logarithm of both sides, we can say that the logarithm of y is a logarithm of 5 to the 7.5 power. But using this property, that's 7.5 times the logarithm of 5, and now that's something that we can calculate. You couldn't do this just by looking at an exponent as repeated multiplications because of that 0.5. But now, provided we can find out what the logarithm of 5 is. Now, how do you know what that is? And nowadays, the answer is plug it into a calculator. But, historically, there was one guy who spent his entire life calculating logarithms of numbers. It's a very difficult thing to do without computers. I don't know when he did this, but hundreds of years ago. And he compiled this table of logarithms that people have been copying since he did it. And that was basically his life's work, and it paid off for hundreds of years. And so we can just say logarithm of a number is something that is known. Okay. So when it comes to exponents, we've turned raising something to a power to multiplication. So, log 5, we can look that up, and then multiply by 7.5. And we've taken this exponent and turned it into a problem in multiplication. Similarly, let's say we have logarithm of, or let's say we want to know 4.7 times 6.2. Not very complicated, we could just do that. But if we take the logarithm of that, let's say that was equal to y. If we take the logarithm of both sides, we can turn this into a problem of addition. So we look up log of 4.7, log of 6.2, add it up, and then we know the logarithm of y. So we've turned multiplication into addition. And if we had division, same thing. We turn division into subtraction. Now again, this doesn't really answer our question because we want, say, 4.7 divided by 6.2. And what we've done by doing the subtraction is we get the logarithm of y. But again, if you have a table of logarithms, you can just work back and get what y itself is. So you need like one table, and you can, like if you know what the logarithm of y is, you can use your table to find out what y is. So let's just look at one practical example. Let's say you want to know the force between two masses. So this involves multiplication, division, and exponents. If we take the logarithm of both sides, I'm just going to write out the answer. Logarithm of g, not 6, logarithm of g, plus logarithm of m1, plus logarithm of m2. And then we're dividing by r squared, so we'd have minus the logarithm of r squared, or minus 2. times the logarithm of r. So again, we look up all these values and then just add and subtract and get the logarithm of the force. Now, one thing that might seem like a problem is, okay, g is 6.67 times 10 to the minus 11. Numerically, that's the value of g. How are we going to look this up on a table? Well, fortunately, we don't need to look up this number on a table. These tables of logarithms just have logarithm of numbers from 1 to 10, and that's all you ever need. Because we know that logarithm of 1 is 0, and logarithm of 10 is 1. So if we wanted the logarithm of g, we can write this, here's a product. So we could say logarithm of 6.67, and then plus logarithm of 10 to the minus 11. Remember, log of 10 to the n is just n. So instead of writing log 10 to the 11, we can just say minus 11. So again, this is something you can find in a table. And yeah, so again, you can find the logarithm of any number. If you know the logarithm of numbers between 1 and 10, by writing things in scientific notation, you can find the logarithm of any number that you want, regardless of the exponent. Now, the reason I'm going through this, even though I doubt any of you are ever going to do this in your lives, it's good to get used to this process because we're going to go to the decibel scale next, and I want you to get familiar with actually working with logarithms instead of just plugging things into a calculator. It's actually simpler, I think, because most of the mistakes students are going to make are when it comes to plugging things into the calculator. So in a sense, you can say that's the most difficult part of it. But if you work it through kind of algebraically, you tend to make fewer mistakes that way. So I think we kind of covered the basics of logarithms. This is all we really need. And so we'll leave it here, and then we'll talk about the intensity of sound waves.